All right, so now let's begin our talk on electrolytic cells. We're not going to spend too much time on this. The key idea is that an electrolytic cell is where non spontaneous reactions that require an external power source occur. Okay. The important features of electrolytic cells is that you don't need a salt bridge because you don't need to balance the charge. Electrons still flow from anode to cathode, but through an external circuit. The power supply pushes electrons to the cathode, so it's not that your anode is providing the electrons, it's that your power source is providing the electrons to the cathode. And then the ion movement is still from cations to cathode and anions to anode. The cathode reaction is still your reduction, but now it's going to be the species that's lower on the table that has the more negative cell potential. And that's the one that's going to be reduced. Whereas your anode is still your site of oxidation, but now it's going to be the species that's higher on the table with the more positive E, which then you're going to reverse and it's going to be negative as well, so that your overall E value is negative. So I find this little chart of a comparison kind of helpful. So an electrochemical cell is a spontaneous reaction. Electrolytic is non-spontaneous. The E value is positive for electrochemical cell versus negative for electrolytic. The electrochemical cell produces energy, whereas an electrolytic process requires electricity. Both of them, the cathode is the site of reduction. Both of them, the anode is site of oxidation. But your SRP rules are reversed. So for an electrochemical cell, your top reaction will be your reduction and your bottom reaction will be your oxidation. Whereas for an electrolytical cell, your top reaction will be your oxidation and your bottom reaction will be your reduction. So same thing too with electrons. The electrons will flow from the anode to the cathode, but with the electrolytical cell, it's the power source that's pushing the electrons to the cathode. But it's still flowing to the cathode, so you don't have to reverse any of that stuff. The only thing we're really changing is that when you pick your species, you're picking an overall E value that's negative, and then you have to force the reaction to occur. So what I wanted to give you next was just an example of a simple electrolysis. So an example of a simple electrolytic cell, which is something that has a molten salt, which means you have a solid ionic compound, so something like a zinc chloride or a sodium chloride, that is heated until it melts. And so you've got these mobile ions floating in solution. So in this example, I've got sodium chloride. So there's these mobile sodium ions and this mobile chloride ions in this solid ionic compound, or some examples are like an aqueous solution instead. This one just happens to be molten, which is a little bit weird, but it's fine. The key idea is that no water is present for this one, so only the metal and non-metal ions are available for reaction. So the only thing here are these sodium ions and these chloride ions. And how it's going to work is that the cations are going to migrate to the cathode and they're going to be reduced to form a pure metal. But the only way this is going to happen is that you get electrons from a voltage source. And so you're electrifying or powering this situation so that your sodium ions can be reduced and form this sodium metal on this inert electrode. So the electrode doesn't, or the cathode doesn't have to be like a sodium metal. It can be any inert metal. Inert meaning that it won't break down, because you just want to have something that you can use over and over again in industrial processes. And then the anode is going to be where the non-metal ions are going to migrate. So your anions are going to go to your anode and they're going to become oxidized, but they're going to form non-metal elements like a chlorine gas. So an example of this is going to be this sodium and chloride. So if we were to look at these on the chart, right? Actually, let's bring up the chart because it can be helpful to have it up. There it is. Okay, so if we look at this, we're going to go that the chloride is going to be oxidized. Now let's take a step back. Let's just find chlorine and let's find sodium. Okay, so on here, where is my chlorine gas? So we want chlorine gas forming chloride minus, okay, this guy. And then we want to find our sodium. Now sodium's going to be way at the bottom, so I got to zoom out. My sodium is going to be way down here. So in this reaction, instead of my top reaction being my reduction, it's going to be my oxidation. So my two chlorides are forming this chloride gas when they release two electrons. So they are still being oxidized, whereas my sodium at the bottom is going to run as a reduction, and it's going to be the sodium is going to gain the electrons to form sodium. Now, because it's not a spontaneous reaction, it's not like you can be like, hey, chloride, you should oxidize and you should give me your electrons. So instead, there is this current that's going to run that's going to provide the reaction for this to occur and provide more electrons. But the overall reaction is going to have this negative overall cell potential. So the requirement would be that since the E is overall negative, it's non-spontaneous, so electrical energy must be supplied from an external power source to drive the reaction. And the minimum voltage is just anything over 4.07 volts, right? So we're ignoring losses like resistance. So they often have to actually provide more, but that would be kind of the bare minimum. And then why would we want to do this? Well, I'll show you some examples in industrial processes, but the key thing is you could have like an impure metal, or you could have ions dissolved in solution that maybe you could use an acid to break down an ore. And you want to take these now ions that are in solution and deposit them as pure metal so that you can sell the metal, right? Because you're probably going to then make batteries. Full circle moment. Anyway, sorry, my own little this is funny. But applications are the production of alkali metals, so something like a sodium and a potassium from their salts. You can also produce metals like aluminum from aluminum oxide, which is a molten cryolite. You don't have to know all that. But the key thing is that this idea of electrolysis, not this molten one an example, but electrolysis itself is for metal extraction because we need metals for a lot of things in life. Okay. So what can I ask you? Well, I can ask you the differences between electrochemical and electrolytic cell, knowing things like spontaneity and the E value and what reaction is happening at the anode and all that kind of stuff is fair game. And then something else would be like these two questions. So it says, what are each of the half reactions and overall reaction for the electrolysis of the following compounds? How much voltage would need to be applied to each cell? So we are going to be starting with, these would be ions in solution or a molten compound that we then want to extract a metal. And the question is, if I have these two things available, so in other words, for this one, you would have aluminum ions and you would have chloride ions. And the question is what would the half reactions be so that we can figure out what voltage would need to be supplied to the cell? So what we're going to do is we're going to go back to this. And now instead of finding chloride and sodium, we're still going to use chloride, but we're going to put this with aluminum. So aluminum is right above the sodium. So unfortunately, I can't scroll back in. So the idea here, again, is that instead of your top reaction being reduced, it's going to be oxidized. So again, you are going to have the two chloride ions producing chloride gas and two electrons, and that is going to be your oxidation. So this is going to be happening at your anode. And then your cathode is still going to be your reduction reaction, but now it's your lower down. So this time it's going to be the aluminum 3+ plus 3 electrons is going to go to aluminum solid. Now I could get you to do things like balance these reactions, but all I wanted to know was how much voltage would need to be supplied. So my E naught for the chloride is run in reverse, so it's negative 1.36. And then my E value for my aluminum is run forwards, which is negative 1.66. So that my overall E value is 1.36 plus 1.66. Negative 3.02 volts. So what does that tell me? So what this tells me, now that I've got the overall, because it says, what are each of the half reactions and overall, oh, I did say overall reaction. Boom, boom, boom. Okay, and we should balance it too. So before I get to there, boom, 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 boom. We should multiply this guy by 3 and this guy by 2. So we balance the electrons, and we would have 4 chloride ions plus 2 aluminum 3+ ions, forming 3 chloride gas. Sorry, I wrote a 4 there and I meant 6. Hopefully I haven't made too many mistakes. I'm on hour 5 of making videos. All right, so 3 chloride gas and 2 aluminum salts. So that would be my overall reaction. My overall cell potential is negative 3.02. So therefore, at least 3.02 volts must be applied. Awesome. Okay, try the next one. So for this one, we have Mn2 plus, and we've got the fluoride ions to start. So how are we going to do this? Well, we're going to go back over here. We're going to look up Mn2 plus. So my Mn2 plus ions. Oh yeah, okay. Let me just get rid of some of these boxes because they're all getting a little bit close together. So here's my Mn2 plus. And then my F minus. I feel like F minus is like at the top, is it not? Yes, it is. Okay, so how's this going to happen? Well, my top reaction is going to be oxidized. So my 2 fluoride ions are going to form fluoride gas and 2 electrons. And it has an E value of negative 2.87. And then my reduction reaction is going to be the Mn2 plus the 2 electrons forming Mn solid. Okay, we have to find our overall reaction. So this one's already balanced for electrons. So we would just have 2 fluorides plus 1 Mn2 plus is going to form F2 gas and manganese solid with an overall potential of 2.87 plus 1.19 gives you negative 4.06. Oops, delayed reaction there. Therefore, at least, or I can just use my symbols, at least 4.06 volts must be applied. Awesome. Okay, hopefully that makes sense. And then the last video is going to be on applications of electrolytic cells.